Hello everyone. In this session, I want to look at how we can use boosting if my response variable is a count variable. So till now if you see we have used boosting where your response variable is a binary variable, categorical, and a multi-categorical kind of a variable, or we have used when it is a continuous variable. We have also used boosting when it is a discrete variable. Now we are looking at how we can use boosting if the variable is a count variable. And again go ahead with the same process. Now in this context, I'm using three different algorithms: the Poisson regression, negative binomial regression, and hurdle regression. Again, all of these, they are going to use the package mboost and the function being glmboost, which we have been using for the continuous variable based regression boosting, as well as the discrete response variable based boosting. Also we have used the same function and the same package. Here also it's not going to be anything different, which means I would use the same code that we have used in these two videos. The same code I am going to repeat. I will copy the same code because only hardly one or two minor differences will exist in the code between the boosting procedures that we have applied in these sessions versus the boosting procedure that you are going to use here as well. But because the response variable is a count variable, the data that I am going to work with is different. I have considered the data relating to a hospital. Right? I have considered the data relating to hospital. So if you look at the data quickly, the dimensions of this hospital data is it contains 4406 rows and 13 columns. And looking at a quick summary of this hospital data, now here we look at the number of doctor visits, minimum of 0 to a maximum of 89. This is what I would like to consider as a part of my response variable. Emergency is going from 0 to 12. Number of hospital stays going from 0 to 8. Health status, average, these many people are there. Excellent, these many people are there. Poor, these many people are there. These are the chronic conditions ranging from 0 to 8. Age ranging from 66 to 109 for these patients. Gender, marital status, the years of education, we have a few completely illiterate kind of people as well. The family incomes going from here to here. The employment status and whether the person has a private insurance or not, Medicaid or not. So we want to really see how many times we can expect people with all these conditions, people with these specific conditions, how many times I should expect that they will visit the doctor. That is what is the model that I am interested in building. Right? I want to link the number of doctor visits. Typically, if you say the doctor visits here is visiting as an outpatient, I want to predict based on the various data that I have approximately how many times will a person visit the doctor, right? Given these all, he has already got into emergency situation these many times, stayed in the hospital these many times, so health status is something like this. Taking all these things into picture, I want to use the various models. The count base, here we are talking of how many times the person is going to visit the doctor. So because it's a count based response variable, I want to use the Poisson regression in this case. So let me go back to the data here. Let me go back to the slide. Try understanding how we can use the same. So the Poisson regression, typically when the response variable is a count variable. So here I am looking at the response variable being number of doctor visits. It's a count variable. So I am expecting that the count variable is following a Poisson distribution with a mean. The mean value for that Poisson distribution, it purely depends on the covariates. And we know that in a Poisson distribution, the mean is lambda and even the variance is lambda, which means the mean and the variance, both of them, they are depending on the covariates in case of Poisson model. But when you are working it in R, something that you realize, we are using the same GLM boost function, the same input variables, the only difference being the family you are changing it to the Poisson. Rest all is remaining the same as you have executed in the logistic regression based model, probit regression based model, or L2 regression, L1 regression, all of those things that you have considered earlier. Now, just for a quick recollecting, let me see the steps. We have loaded the mboost package, got the data into R where the response variable is a count variable for me. I have built the relationship between the response and the attributes. So here I will consider all the attributes. So I will continue in the same way. Then the split. I have to split the data into a training sample and the testing. So here the first column is my dependent variable and all others are my independent variables. Right? So now I have to split the training data. So we know that there are 4406 rows out here. Then I can simply set the seed first of all to 1000. Then I can use the train as a variable, sample 1 to 4406, where I want 70%. So typically let me take 4406. Oh, I need to know how many. So for quickness, let me consider 3406 as a part of the sample training data. Remaining 1000 I will use for the testing purpose, right? And replace, I am setting it equal to false so that there is no duplication involved. So from here I am creating my training data, which is a subset of hospital, which takes the rows that are there as a part of the train and it contains all the columns. Then I will also consider my testing data, which is also a subset of hospital. It contains the rows which are not there as a part of the train and it contains all the columns. So I am going ahead with these two things out here. I have created a training data, I have created a testing data. Now I am ready to fit the model. So to fit the model, let me use the code that we have used earlier, GLM boost. Here the dependent variable for me is doc underscore visits. That's my dependent variable. Tilde dot. Data is train data. Controls, the boost controls, I am setting them the tree size, the depth, and number of iterations. All those things I am setting them, or even the new. All of them I am setting out to be the default values itself. So I am not changing any one of them. Now the family here, I have to change. The family, I am going to change it to Poisson. So instead of binomial with this, I will change it to Poisson with nothing inside it. I am changing this to Poisson. Coefficient of, so I can very well get the coefficients of the fitted model. After that, now look at the process. right? Now, once I have broken the data into a training data and a testing data, I am fitting the model using the GLM boost. Maximum number of iterations here I am setting it to 100, but again I should change it depending on the where the error is coming out to be the minimum most. Even the shrinkage parameter by default, I'm retaining it, which is the default behavior itself. So based on that, I will look at the coefficients of the model, which is there as a part of the code. Then I am going ahead into the 10-fold cross validation, where the whole data will be broken into 10 non-overlapping parts. The model will be built using 9 of them, and it would be tested on the 10th one. And this process is repeated with all sets of data, so that the cross validation error could be a much better reflection of the accuracy of the model. And it will also tell me what should be the optimum number of iterations. Right now by default I am going with 100, but it might have been very much possible that the error would have been much lesser at a lesser number of iterations itself. So this model helps me to understand what should be the optimal number of boosting iterations I should perform, and that is being assessed by the risk function. The risk is computed at each of the layers. Empirical risk is computed using the CV risk function, and wherever that particular risk is the minimum most, that is where the model suggests that I can stop the number of iterations, and that particular model will be typically used for the prediction purposes. That is how the whole thing is. So up to here the process is more or less similar to what we have done in case of the other models, other regression models. So for the coefficients, I can even build a 90% confidence interval. But if I have to build it, it's better that I set the bootstrap sample to very large value. But if I am setting it to a large value, the time for execution will be much higher. So I may have to really have in real time. That's very much okay in the real world when we are solving business problems. But whereas here I would like to set it to either 50 or 25, or probably I may omit it altogether. You can very well go ahead in terms of using the conf int kind of function which we have used earlier in regression, by setting the bootstrap sample size to at least 1000, so that you can get the confidence intervals associated with the various coefficients, and you can very well check whether all the covariates are statistically significant or not. Then once the model is good enough, you go ahead in terms of predicting the model on the test data, evaluate the accuracy of the model. So the process remains more or less the same. So what I will suggest is I'll go ahead in terms of creating this model, executing it in R. Okay, this model GLM boost, where it has gone with the Poisson family distribution. Now I could see the loss function is minus dpoise. So this is the loss function that has been computed out here. I could see here almost all the variables are being included. Emergencies, hospital stays, right? Health status, excellent. How many variables? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 variables are included as a part of the model, right? Even if you look at the total number of variables itself, 1, 2, 3, 4, 5, 6, 9, 12 variables are there, and the independent variables are 11. And here I see 12 variables being included. Medicaid S is included, private insurance is included, employed or not is included, family income is included, years education, married yes, gender male, age. Looks like almost all of them have been included in the process, right? This is the model that is typically being built. These are the coefficients that are included as a part of the model. So even if I say coefficient, I will get the coefficients associated with the model. Then I can look at tenfold cross validation of it to understand what is the optimal size of number of iterations in the model. When I look at this fit CV, which has used the CV risk function for assessing the number of optimal iterations, I could see that the error 4.39, 4.29 came down to 2221, came down to 205, after that 205, 204, 206. So after a certain number of iterations, at least it started increasing the value, which is clearly saying here the optimal number of boosting iterations is 19. So it is at this 19 where the error has gone down to the least possible, right? So it has clearly given me that at 19 iterations, the error of the model has gone down to the lowest. You could look at the plotting of this, you could clearly see that at 19 iterations, the error is lesser. Of course, even after that, the error is much lesser itself. But the least error has actually come out at 19 iterations. So this is where I can even find out when to stop the whole iterations. It says at 19th step you can stop the whole iterations. Based on that, I can find out the coefficients associated with my 19th of iteration. I could see in this case, after the 19th iteration, the number of variables have typically come down, right? Emergencies, hospital stays. I don't see now emergencies as a part of the model at all. The doctor visits is based on hospital stay, health status excellent, health status poor, chronic conditions, age, gender, years of education, private insurance versus the presence of Medicaid. So this is a much better function as a part of this model out here. Now I can very well look at predicting this model for the test data as well. Now once I have predicted this model, the predict, it is giving me the values that are associated. I could round those values because here it should be more like we are talking about the number of doctor visits. The model has computed more like this. These are the predicted values that have come out of the model. Right, there are 11, 16, 14. So these are the different values that have come out of the model based on this prediction. Now what I can very well do is for all these 1000 observations I got what will be the approximate number of doctor visits. So I can very well say pred as I will do a rounding of pred to 0 digits after the decimal point. So based on that, if I look at my pred, I will get exactly how many visits are being taken in each of the cases. Based on that, I can evaluate what is the level of accuracy of the model by comparing it either with the R squared. I'll take the predicted value and the actual value is coming out from the test data, all the rows first column. So based on this, when I'm looking at the accuracy of the model is hardly at around 13%, which is much lesser. Or probably if I'm going with the confusion matrix, the table, I could very well go with the confusion matrix as well, where I'm looking at the predicted value as well as the actual value with this. Even this table is giving me a confusion matrix like this. So if I look at the accuracy, it is hardly, here we have only these values being predicted, whereas the actuals, these are the values. So probably it's better that I go with the R squared itself rather than relying on the confusion matrix to compute the error rate. The correlation has simply provided that it is only 13%. So this model could not identify the best possible relationship for understanding what would be the approximate number of doctor visits that are going to occur for each of the patients. So even you can very well assess what is the importance of each of these variables by going ahead with the confidence interval. But you are at least able to make out here which of the variables are significant and which of the variables are insignificant in terms of understanding how many visits that a person is going to make to a doctor. So that's how we can understand this Poisson regression model. So in this case, when I am going with a Poisson regression, the correlation or the R squared, did I take the R squared? Yeah, R squared is coming out to around 13.06% only. Now I want to try with the same data whether the other models, which is the negative binomial regression model that I have used or the hurdle regression, they also differ very slightly. So one of these two models, are they going to improvise our overall accuracy of the prediction? Negative binomial regression generally is used when the count variable itself is over dispersed and you have two extreme kind of values, which is real in this case where I have one person going for 89 visits altogether. So there is a lot of over dispersion with respect to the count variable. So there is a possibility that compared to a Poisson regression, I may very well get a benefit using the negative binomial regression here. The only difference being, instead of Poisson, I will set this as n binomial. So let me change the code first. Instead of Poisson, I will change it to n binomial. That's the only difference. Probably if you read through it, the code, okay, we have loaded the package, got the data, training and testing data. We are using GLM boost, coefficient. We are talking about tenfold cross validation. Check the parameter estimates, optimal fit, do the prediction wherever necessary, compare the predicted value with the actual value. So the steps are more or less the same. So I want to quickly go ahead, execute this negative binomial based regression boosting and see if the results are going to be anywhere better. So for this data, the response variable, now I am assuming that it is following a negative binomial distribution rather than a Poisson distribution. And based on that, I am trying to do the fitment. Even this fitment with 100 iterations, right, it has gone ahead in terms of identifying these as the important drivers: emergencies, hospital stays, health status excellent. So it looks like, okay, more the number of emergencies, more the doctor visits, more the hospital stays, more the doctor visits. But if the status is excellent, lesser the number of doctor visits. Status is poor, looks like more number of doctor visits. More chronic conditions, more the number of visits. Males, slightly less number of visits compared to that of females. The higher is the education level, looks like higher the number of visits to the doctor. And the private insurance, more the private insurance exists, more the number of visits, because the insurance company will typically pay for them. Similarly, if someone is having Medicaid also, they are visiting the doctor more compared to the people who do not have. So that's the basic understanding that we have got from this high level model. So let's see, if I want to reduce the, if I want to look at the optimality in terms of whether I require 100 iteration or in which case the error is the least, right? In which kind of are 100 iterations typically required, or probably somewhere in the middle itself the error has actually come down. We are trying to do a tenfold cross validation to understand where the error is more or less minimum in the entire process, at which iteration after which iteration I should stop this overall process to understand where the error is the minimum most. So I am trying to run this tenfold cross validation, storing the results in FitCV, using the CV risk function. So let's try to see the results of this model. So the result that fit CV is giving to me. Okay, the error wise, in the first iteration the error was 2.83, 837 came down to 833, 828, 823, 820, 816, 813. So it looked like it took all the 100 iterations. So in the 100th iteration only the error is the minimum was. So whenever such kind of scenario has occurred, it's a kind of a pointer for me to try out more number of iterations. It means that if I execute even more number of iterations, let's say 500 or 1000, it might be possible that somewhere I would get a minimum and from there it could start increasing. So I am more interested in repeating the iterations more and more. If at all I am ending up with the optimal number of iterations occurring at 100. But here for the purpose of understanding, I am not going any more further. So even if I am doing a plotting of this, I am not getting the minimum error somewhere in the middle, but only towards the end is where I am getting the minimum number of the minimum error. So that is what is an indication that overall I should try to increase more number of iterations to improvise the accuracy of the model and reduce the number of errors. So even if I use this M stop, it says that you should stop at the 100th iteration itself because that is the one that is giving me the least possible error altogether. So now if I try to do the prediction based on that, so these are the predictions that are coming out. I can look at the pred. The pred has given me different kinds of numbers out here, right? It has given me the estimates of different number of days. So I can very well look at pred as a rounding of the pred value to 0. So which has given me the pred values as these kind of numbers, wherein I can take the correlation between the predicted value and the actual value coming from the first column of the test data. I am taking the correlation squared, the R squared, to understand the fitment between the predicted and the actuals. Here it has resulted in only 11.96% being the accuracy of this model. Right, negative binomial regression has resulted in only 11.96% accuracy on the test data, whereas the Poisson regression has resulted in 13.06%. So when I'm comparing these two models, it looked like the Poisson model is much more appropriate for this data compared to the negative binomial regression model. Similarly, I have one more model which I can work with, which is also on the same lines, which is the hurdle regression. If you see here, even this I am using when there is over dispersion and if there are excessive zero counts in the data. If the counts are zero, more number of zeros are there in the data, then it's better to use hurdle regression compared to either a Poisson regression or a negative binomial regression. And again, in this also the major difference that comes is within the GLM boost, I am setting the family as a hurdle family. Rest all you could see the process is exactly the same. So this is where in the model I will change it to hurdle. That's it. I can again go back and fit the model using the hurdle regression now, because under the assumption that there are so many zeros as a part of the model and there is a lot of dispersion in the model, under those assumptions I can think of fitting a hurdle regression model. And when I am looking at it, wow, this model, except the intercept, it did not consider anything as the drivers. So it's a very clear cut thing that there is nothing much that is coming out of this model in terms of estimating how many days the doctor, how many doctor visits are going to happen, because no other variable is playing any kind of role in determination of this particular model. So when we have run all the 100 iterations, it looked like nothing is impacting. Let me just check through the cross validation, tenfold cross validation, if there is any kind of intermediate number of iterations where things were much better, right? If for probably 30 or 40 iterations, at least some key variables are being considered. I want to look at it if the error is the minimum most somewhere in the intermediate layer rather than towards the 100 itself, which required more number of iterations to be typically performed. So let's look at fit CV to see if there is any other intermittent layer in the overall process. There is a possibility that I may have to increase the number of iterations quite drastically. 100 may not be a good indication of the number of iterations, so that's where I may not be getting a good solutions here. But here our objective is more to understand the models, understand the significance of using each of these processes. So it should be okay even if we are going with a smaller subset altogether, right? So let's see if there is any kind of an improvement, or let's understand how many errors are coming out. What is the at what number of iterations is the error minimum most after the tenfold cross validation that has occurred. So if I am trying to test what is fit CV, yes, the error has started at 2.15 with the first iteration. There is a very small gradual fall that is occurring, and you could see that the optimal number of boosting iterations is 100 itself, which is again an indication that I have to increase the number of iterations so that I'll get a much a better scenario where somewhere for the middle number of iterations the error is minimum. So increasing the iterations as well as decreasing the iterations is going to increase the error. So when I get into that kind of a scenario, that is when it would be a more optimal for me to stop the number of iterations. So here, stopping at 100 iterations is a simple meaning that the number of iterations are not sufficient for the model to be overall optimized. So even if I am plotting it, this is how the error function is looking like. It's coming down, and only in the last it has come down drastically. So just for the sake of understanding, let me try m stop. Let me just set it to let's say 2000. Just for the sake of trying, I want to showcase this to you. I'm setting the number of iterations to be 2000 in the original model itself. Let's see with the original 2000 how accurate the model is going to come out when you are going with fit CV on the top of that. When you are going with CV risk on the top of that, is it that even up to 2000 your errors are going to come down only, or somewhere in the middle you see that after a certain number of iterations the errors may start going up? Let's observe that scenario as well, right? That means you could do the same things even for other data sets in the real world. So let it execute for all the 2000. Instead of 2000, I should have tried at least 500 to start with. Let me do that. Instead of 2000, instead of 100 or something, let me try with 500 to see if things are improved. Now looking at with respect to 500, this is how the model came out. I could see now when the coefficient, when we are talking about 500 iterations, at least some variables started coming into the model. Now this is what is the difference that I am talking of. Sometimes it might be required that you may have to go with more number of iterations, right? Now, if you want to go with a cross validation, tenfold cross validation on this, there might be a different scenario altogether. Compared to 100, we have seen in 100 we did not get any variable being included as a part of the model. But when we have done 500 iterations, we are able to see that emergencies, hospital stays, hospital status, chronic conditions, years of education, and the presence of private insurance, they have contributed to the number of doctor visits. You could also see that the hospital stays, more the number of hospital stays, more the doctor visits. If the health status is excellent, then the lesser the number of doctor visits, more chronic conditions resulting in more number of visits, and more private insurance being present is also resulting in more doctor visits. More number of years of education looks like slightly higher in terms of the number of doctor visits. So realistically, the relationship between the variables got modeled, but now we want to see what would be the appropriate number of iterations where I would get the least possible error out of all the number of iterations, so that I can use that particular model for my prediction purposes as well. So the tenfold cross validation on 500 observations on 500 iterations is typically taking a good amount of time compared to doing the same with 100 iterations. But still, I am expecting that somewhere in the middle we should get much lesser amount of error rather than it saying you have to continue beyond 500 as well. So let's wait and look out for the result. So it has taken a good amount of time to complete the whole process, but nevertheless we can very well see what is the level of what is the level at which the error is the minimum most. It has still shown that at 500 iterations itself the error is the minimum most, which means I should actually run few more iterations altogether. So even at 500, I am not able to come out with anything, but at least some number of variables are typically influencing the overall response variable. So this is telling me that you have to stop at 500 itself. Based on this, if I am going with the predicted value, so these are coming out to be my predicted values. Using this, I could see that this is how the predicted has typically come out. right? Using this model, this is how the predicted values have typically come out. Looks like if I remove this response, how will the predicted values look like? Let me look at the pred. Okay, the predicted values are lying in a particular range. Now I need to actually bring them back into the original. So this is where I can look at performing the correlation directly between the predicted values and the actual values to see what is the level of accuracy in the model. So if these are the predicted values and the actuals are coming from test data dollar, I mean test data and the first column of the test data, I look at the correlation square R squared between them. Even in this case, it works out to be around 11.58% itself. Even in case of hurdle regression, the accuracy is working out to 11.58%. The same case was there in negative binomial 11.96, whereas the Poisson was showing 13.06. So again, we could have used any one of these models for doing the prediction based on the understanding of how the response variable is, what kind of relationship the response variable is typically carrying. Well, so these three models should help you to understand that I can still use the GLM boost function from the mboost package to model a response variable which is a count variable, I can use it very well to estimate the number of doctor visits or some kind of count related variables, and I can run boosting on the top of it as well. So I hope you got fair amount of idea on how we can use boosting for those variables which have count related response data. If you have any further queries, you can again get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pagegurus.com. Thanks a lot for listening to this session. Thank you very much.